What's the fundamental difference between metals and nonmetals?
Non-metals want to gain electrons and metals want to lose electrons.
That's it. And I know some of you went through the luster and malleability, and that was a couple modules ago. Now we're talking about fundamental properties, atomic structure, what's different about metals and nonmetals. Metals want to give up electrons, nonmetals want to receive electrons. Okay? And they're both trying to obtain the ideal configuration. They're both driving towards having 8 valence electrons. Metals do that by shedding electrons to reduce down to 8 valence electrons. Nonmetals do that by gaining, pulling other electrons to themselves so that they can raise up to 8 valence electrons. All right. Number 7. So pass. Critique this statement. The number at the top of the column of the periodic table is the number of valence electrons that all elements have. Is this true or false? And if it's false, why?
I was kind of confused by this one, so I just put that it was correct.
Okay. Consensus. How many people think this is a true statement? Okay, sin boldly. Let's go. Okay, we'll make it easy for you. Close your eyes. This is for me, not for you. So everybody close your eyes. Just pretend like we're in chapel, okay? If you believe this is a true statement, raise your hand. Okay. And if it's a false statement, raise your hand. Okay, and if you're confused and don't know, raise your hand. Thank you for your honesty. You can open your eyes. I'll be standing at the front later. As you leave, you can come talk to me. No. Okay, so the number at the top of the column of the periodic table is the number of valence electrons that all elements have. First of all, it's false. Okay, it's a false statement. Why is it a false statement? Well, you could misread it and say that all elements have. That's a poorly worded question in my opinion. But what are they driving towards in here? The column A, the A columns have. For every element in a column, if it's column 1A, 2A, 3A, 4A, 5A, 6A, 7A, or 8A, then that number for that column represents how many valence electrons that element has. What about the B columns? 1B, 2B, 3B, 4B, 5B. All of those elements have 2 valence electrons in the s orbital, right? Because when we get to the Ds, we reduce down an energy level, and we're filling an energy level that's less than the highest energy level, so the valence number stays the same. So for columns 1 through 8A, it is true that the number on the top of the column represents how many valence electrons are in every element in that column. But for the B elements, column 1B, 2B, and so on, it does not represent the number of valence electrons in that atom. Sir?
For this, I kind of knew, I didn't know exactly how to say why, but not all elements have the same number of valence electrons.
Right, and that's because you were misled by what I think is the poorly written statement at the bottom, where the number of electrons that all elements have. All elements have a different number, so there's a part of this statement which you've got to kind of read through. What are they really asking? So I understand it's a poorly worded question. But do you understand what they're driving at now? If it's an A column, 1 through 8A, it does represent the number of valence electrons in the atom. If it's a B column, it does not. Pass and answer. Here we go. What's the difference between an atom and an ion?
An ion is an atom that has taken a lot of electrons becoming charged.
Right.
And an atom uncharged.
They're neutral. Uncharged is really not the right word to use. Atoms are neutral because they have the equal number of positive and negative charges, so they're net neutral. They have as many electrons as protons, so for every negative there's a positive. For every positive there's a negative, okay? So, an atom is neutral. The ion, and he's correct, an ion has a charge, which means it's either gained or lost electrons. Remember, if it gains or loses protons, it's something different. It's another element. If it gains or loses electrons, though, it's an ion of that element. So ions have a net charge because they've gained or lost electrons. Atoms are net neutral, and they have equal number of protons and electrons, an equal number of positive and negative charges. Okay, go ahead and pass, and here we go. Number 9, what is ionization energy? to take an electron away. Remember, ionization energy, I want you to visualize on ionization energy trying to hold on to something. Now, sometimes it's worded which one will require more energy to take away, but that's in relation to how much that atom is trying to hold on to it, right? So for ionization energy, I want you to think in terms of how hard is that atom trying to hold on to something, and then by virtue of that, that would be the amount of energy that would be needed, that or more, to take it away from them. So it's the amount of energy needed to take an electron away from an atom, or you could say it this way, the amount of energy that an atom exerts to hold on to what it has, the electrons that it has. So it's kind of perspectival. The other one is electronegativity. Electronegativity, I want you to view it from the perspective of the atom that's trying to take and become an ion. So how much force does the atom exert to take away or steal a neighbor's electron? That's electronegativity. So when the electronegativity of one atom is greater than the ionization energy of the other, the electrons transition, they go. Think of it this way. When a neighbor is pulling on something that they want that's yours more than you're willing to fight to keep it, they'll get it. So that's the play between ionization energy and electronegativity. You may at times hear ionization energy as ionization potential. Remember, potential is another word for energy. So if you see ionization potential or ionization energy, it's the same thing. I'll try to make sure you get the consistent terms of ionization energy, but that they're speaking of the same thing. Okay, pass and go. Name 3 periodic properties of atoms.
Atomic radius, ionization energy, and electronegativity.
Right, those are the 3 we covered. Ionization energy, electronegativity, and atomic radius. Now we're going to review it tomorrow just by the homework, the way I broke it down, but the next question asks how these different properties trend. Okay? And even though we're going to do it tomorrow formally on a slide, what is the trend of each one of those? Ionization energy, it increases as you move up and to the right. Electronegativity increases as you move, again, up and to the right. Good. And atomic radius increases as you go down and to the left. So up and to the right, down and to the left. Atomic radius is counterintuitive. If you just remember that atomic radius is the odd person out, or odd one out, and the other 2 go up and right, just reverse the head on the arrow. All right? Okay, pass and go. Here we go. Practice problems. Yay. And we'll make sure everyone gets a turn before we get doubles, okay? So if you get stuck with a double, we'll check real quick to make sure everybody's had a turn. Practice problem 4. Order the following atoms in terms of increasing ionization energy. Who's answering this one? Birthday boy, okay. So before we answer this question, actually, no, we don't have to reword this one. This is good. Okay, so we're going to go ahead to the periodic table. What are we going to do first? Locate them on the periodic table. So we're looking for, in order, SR, SB, I. Oh, sorry. It had all those forwards built into it. There, take it away real quick so we can logic through it. Here's the way it's supposed to work. SR, SB, I. What is the periodic property we're looking for? Ionization energy. The trend is up and to the right. Okay. So based on this now, up and to the right, you've identified them, you've noted the trend, and the question is to place them in, let's see, increasing ionization energies. So your answer would be?
SR, SB, I.
Okay, do you see? Everybody see where that's coming from? We're moving up and to the right, so our trending is this way. They increase in that direction. So we go from low to high, and this is the right way to write it. SR, in terms of ionization energy, SR is less than SB, which is less than I. So in order of increasing, and I know many of you did SR, SB, I, that's fine. I mean, I understood what you're getting to, but I want you to start writing it this way, not just simply with commas. SR, SB, I would be in increasing order. That is true. You answered the question correctly, but just get used to recognizing by using greater than, or less than. This is less than this. This is less than this. The other way to say it is this is greater than this and this is greater than this. Okay? So that's your order, that's your trending based upon the location on the periodic table for this periodic property. Pass and go. I guess it's not really pass and go, it's pass and answer, right? Pass and go with the question. How's that? That's what I mean by it. All right. Which atom has the greatest desire for extra electrons? Now, this is one I want you to try to reword. What are they really asking here? And put it in terms that we've been studying. If something has a desire for extra electrons, what is it really asking us? Very good. Which atom has the highest electronegativity? Do you see that? Okay, again, looking from the perspective of the atom, the more I desire to have more electrons, the more force I'm going to use to take those electrons. That's called electronegativity. Okay, so which of these three has the highest electronegativity? Okay, well, we're going to do the same thing again, right? Let's go ahead. Nitrogen. There's N, Sb, and As. Okay, so we've located all three of them on the periodic table. What is the trend for electronegativity? Up and to the right. So we look at the plot, we look at their locations on the periodic table, we know the trend is increasing up and to the right, and so the question was, again, let me go back and read it, which has the greatest desire for extra electrons? Nitrogen. It's the highest and the rightest of those. So it has the greatest desire. That tells me that of all these, let me back up one slide. Of all these three, they're all going to exert energy to get more electrons. But because nitrogen is higher up, it's going to exert more energy to get somebody else's electrons than astatine or Sb would. It's going to exert more energy than they do. So we're not saying how much they're exerting. All we're saying is which exerts more. So if I had the option of using these three and I needed a chemical reaction where I wanted to make sure that this nonmetal was going to rip away electrons from my metals, I'm going to go with nitrogen. Okay, because it has a greater electronegativity, greater force to grab electrons and steal them from their neighbors. Putting real dramatic terms like that. It's going to rip it out of their hands, right? So nitrogen has the greatest electronegativity, or the greatest desire for extra electrons. Number 6, order the following atoms in terms of increasing atomic radius. So, we don't need to reword this one, right? Okay. Just go ahead and, I should, for this one, I kind of walk you through it, but let's go through it. We'll do the process, and then you can give me your answer. So look, periodic table, let's go ahead and plot or find the location for all of those atoms. Okay. So we locate all 4 of them on the periodic table. Now, what is the periodic trend for atomic radius? Ma'am? Okay, so the trend is down and to the left. Down and to the left is increasing. So the atomic radius is increasing the farther down and the farther left you go. So we look at the 4 that are plotted, and we're going to put them in the order of increasing radius, right? So what would the increasing radius order be?
Question.
Yes.
In the book, it says that the elements are As, K, Br, and Se, not Sc.
Yeah, that's what I got too.
So it's SE
I mean, it's
instead of
not
SC,
really.
but I mean.
SC as opposed to SE, or SE as opposed to SC?
Yeah.
Okay.
Still.
Okay.
I mean, it's not that big of a deal. I just don't want to get it wrong.
Right, I mean, we're changing.
Yeah.
Other ones right between the
Yeah, it may have just been me putting the, yeah.
Birthday's ruined.
Either way, you probably got it wrong.
Okay, let me look at, it's a misplaced arrow. Okay, so let's do this one with the arrow should be over here at SE, right? So we're talking about BR, SE, AS, and K. Okay. Given that, then, what is our order?
B-R-S-C-A-S-K.
Right. It's a misplaced arrow. I have to work on a PowerPoint slide that has it really small, that has inside that, and so I'm like moving the arrow, and I can't even read the letters. I'm guessing half the time where these things are at, so I apologize for that. With these eyes and these buys. Okay, so BR, and we're moving, this case here, we're all in one row, right? So this is purely a left directional, right? We're moving to the left. And so as we move to the left, we know the trend is increasing. So it's going to be bromine is smaller than astatine, is smaller than selenium, is smaller than potassium. Remember, the reason for this trending that from left to right becomes smaller is because we're not adding any more energy levels. All we're doing is adding negative electrons to the same energy levels, and we're increasing the number of positives in the nucleus, the protons, and so there's a greater concentration and a greater force without increasing the energy level, so they tend to pull in tighter. So moving from left to right, the radiuses decrease. Moving from top to bottom, since we're adding energy levels, like chunk, 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 chunk. And that's not technically correct because I know we're using quantum mechanical as opposed to a Bohr model, but that's a way to visualize it. Every row down is an increasing energy level. All right. And this is the way I graded it, not this, just so you know. That was just a misplaced arrow. So where are we at now? Who? You need to pass? Who hasn't yet had ops? Okay. There's several parts to problem 4, extra practice problem number 3. This is one really that kind of fit better with what we did yesterday. We ran out of time, so I put this in this place in our review. So we're going to, what's the chemical formula for chromium 3 chloride? No, Alexis has this one, I believe. So chromium 3 chloride.
Can it be chromium Cr?
Yeah, so the two elements in play are chromium and which the atom that chloride comes from is chlorine, right? So we're looking at chromium and chlorine. So like I did yesterday, we kind of got into a rhythm. Okay, here's the name. What are the elements in play? Chromium and chlorine. Okay, it's an ionic compound, so we don't just look at the elements that are in play, we now have to look at what ions are in play. So what does chromium become ionically?
Cr positive 3.
We know it's positive 3 because we know it's positive because it's metal, but we know it's 3. And we can't get that number 3 from the periodic table because it's in a B column, right? Chromium's a transitional element. It doesn't play by the A column rule. But we know it's a positive 3 because, well, wants to lose, so it's going to be positive, but how do we know it's a 3? They give it to you. It's right there. Because it has a 3, okay? So it's a chromium 3 plus because we know it's a positive because it's a metal, and they've told us it's going to have a charge of 3, so it's a 3 plus. What about chlorine? Becomes chloride. What's the chloride charge? Negative 1, right? So 1 negative. So chromium 3 plus, chloride is a 1 negative. What is the formula then for potassium, or excuse me, for chromium 3 chloride?
CrCl3.
Yep, CrCl3. And the mathematical check for that, knowing they're going to be opposite signs, but we need to make sure the magnitudes are the same, is that I have 1 chromium ion at a +3 charge, and I have 3 chlorides at a 1 negative charge, and since that statement is true, it's neutral, and we're done. All right, next one. Pass it, and here we go. Zinc 1 sulfide, the atoms in play.
Zinc and sulfur.
Zinc and sulfur, good. The ions in play. Zinc is going to be 1, what is it, positive or negative 1? Okay, you've given me both answers, 1 twice and 1 once. So pick one and sin boldly. Here we go. Zinc is going to have a charge of?
1 negative.
Okay.
Oh.
Zinc is a metal.
Positive. Good
Zinc is a metal, so it's losing electrons to become positive, and has a charge of 1 because it's a transition metal, of 1 because they've told us it has a charge of 1. Sulfur is a column 6 element, right? So it wants to gain 2 more, so it becomes a 2 negative charge. So the zinc and sulfur are the atoms in play. Zinc plus 1 and sulfur 2 minus are the ions in play. How do these combine to form zinc 1 sulfide?
Is it gonna be zinc 2s?
Yep. Zinc 2s, or zinc sulfide, zinc 1 sulfide. Let's check it. 2 ions of zinc at 1 plus is 2. 1 ion of sulfur at 2 negative is 2. It's true, we're done. Okay. Here we go. Pass it.
You weren't going this time, dude.
The formula for titanium 4 phosphide.
Titanium,
The-
phosphorus.
Titanium and phosphorus, okay? The ions in play.
4 and negative 3.
Right? Titanium is a column 4 element, but it's a metal, right? So it's going to lose its 4 rather than gain 4. Carbon wants to gain 4, titanium wants to lose 4. Phosphorus is a column 5 element, it wants to gain 3, becomes a 3 negative. These combine to form what?
Titanium 3, P4.
Titanium 3 phosphide 4, right? Ti3P4. Do the check. 3 ions at 4 plus, that gives me 12. And 4 ions at 3 plus, that gives me 12. They check. Okay. Here we go. Order the following atoms in terms of increasing ionization potential. See, there's the term right there, ionization potential. If you see ionization potential, ionization energy, it's the same thing. So, order them in terms of increasing ionization potential. I should probably get on the right place in my notes, right? We're in EPP 404. Okay. First step, again, I'm not going to have you, who's answering? Okay, I'm not going to have you come up here and spot them, but let's see, SR, RA, and MG. We're talking about ionization energy, ionization potential. The trend is up and to the right, okay? So in order of increasing, it would be that's it. So because it's increasing to the right, increasing up, and here it's all in a column, so they would increase up, the least, the middle, and the most. And that's what that shows. Okay. You want to pass it, ma'am? I'm going to this one. Or who's next? You're answering? I have a quick change there. Okay, so which atom has the greatest desire for extra electrons? Let's reword it. What would the rewording sound like? Which atom has the highest electronegativity? Right, or the greatest electronegativity. It desires them, it's willing to fight for and use force to get. Which one put them in, or which one has the greatest desire to get, right? So those are the 3 elements, and as we've done before, process-wise, you would take the periodic table and you would locate all 3 of those elements, okay? Then you'd ask yourself the question, what is the trend? And in this case, the trend is up and to the right. So the uppermost, rightestmost is going to be the one that you're going to choose as having the greatest desire. And in this case, that answer is bromine. Yep. Okay. Extra practice problem number 6. Order the following in terms of increasing atomic radius. This is yours, ma'am? Okay. So, again, no real hard part here. The hardest part is probably locating them on the periodic table. And I have to do that for you here rather than have you come up and like show me where they would be. So, let's do this. So they place out in a single row. Now we're talking about atomic radius increasing. The trend is
Down to the left.
down and to the left. So in order they would be